All right. So perhaps get rolling. So this is the last thing we'll talk about this half semester. After the break, we'll come back and talk about modeling for one session and then site investigation. So this is the last of our behavioral items, I guess, that we're dealing with. So I just copied this lower part from what we had previously, maybe just to summarize what we've got. So you know that this is what we've talked about. You know that we solved the advection dispersion equation for this. I won't write it down. You know that retardation factor is 1 plus the density of the aquifer divided by volumetric moisture content and distribution coefficient, K sub D. You know it's always greater than 1 unless no top end, but functionally I guess we saw that maybe the top ends were 30-ish. We know what it means. It's equal to the velocity of a conservative solute over the velocity of a non-conservative, or I guess as it turns out the reciprocal of their lengths, right? So it's knuckles. So longer distance traveled relative to non-conservatives traveled less. And so is that the lengths traveled? Yes, the ratio of the lengths traveled, right? Length conservative and the length non-conservative. Yes, this will always be longer. So in the same ratio. And so from this we want to get K sub D. We can get that from natural gradient tracer tests, but we can also get it from organic carbon partition coefficient and the fraction of organic carbon. If there's enough, if there's more than 0.1% organic carbon. And if not, we don't get a very good result because this assumes that all the sorption occurs on the carbon. And so if there is no carbon in the aquifer, then it will predict KD is 0, but of course you could sorb stuff onto the quartz, and so that's the reason that it gives you an erroneous number. And I guess our parting shot was that the total mass that you have in a plume, you're all getting ready to run from here, screaming last time as we were talking about that, is going to be the volume of the plume, its porosity. So these two things together is the volume of water in the plume. The concentration, whichever that is, and that might be the solubility. Or it could be the effective solubility, right? We talked about the effective solubility, which is equal to the mole fraction times the absolute solubility, Raoult's law. And this is what you've used before, right? You've talked about a volume in the water and it has a concentration, so you multiply that volume by its concentration, that gives you a mass of solute. But we talked last time about adding the retardation coefficient to this, which is always bigger than 1. And the reason for adding that was, I'll come back to this very last idea here, don't have it. Where is it? Oh, this one here. Yeah. The idea is that the total mass is going to be the stuff that's dissolved in water, which would be this. This is the total volume, porosity times the total volume of the plume. In turn, inside the aquifer is the volume of water, and the concentration would give you the mass that's messing around in the water. But if that water is in equilibrium with the solid which it surrounds, then there's also going to be stuff sorbed onto the solid grains. And so if you want to include that, you need this extra term. And if you substitute the definition of the distribution coefficient for C star, the amount on the solid, it actually ends up being 1 plus this term here, which very conveniently works out to be this extra added portion. So if you want to account for the stuff that's sorbed onto the solid substrate, which isn't in the fluid, then you need to add this amount. Because as you take the fluid out and you flush it with clean water, for instance, the stuff that's sorption is a reversible process. The stuff that's sorbed onto the grains will come back into solution and will be available to be taken out of the aquifer. So that's kind of a recap of everything we talked about. So this term here would be this, both ways. So that's what we talked about last time. So we'll draw a line under that, and we'll talk about what we'll deal with today. So we're now talking about transport in the vadose zone, above the water table where it's only partially saturated. So we have to talk about the mobility of water in that part. It won't be very mobile as vapor in the saturated zone for obvious reasons. And we can talk about the mechanisms by which it travels, by diffusion, which is one mechanism, I guess by being washed out by rainwater as it passes through the vadose zone as advection, aqueous advection, and we won't talk about natural advection. And again, we can talk about partitioning, how the solutes partition in the water, solid, and now air in the vadose zone, and what the effects of that are on delaying its transport through the system. So that's what we'll chat about. And we talked about the reason for using retardation coefficient and looking at these flow down an aquifer and also the residence time distribution curves. So this is what the model is. So we know that to get to the water table, if we're spilling from the surface, it has to go through the vadose zone. Good Canadian, even though Canadians are out of favor in the US these days, good Canadian spelling. This again represents the fact that this will be locked up in the unsaturated zone, this smear within the partially saturated zone. And if it's present there as free phase, it can volatilize and diffuse, just as it could do an odor within a room. It can dissolve into the water that's present in the partially saturated zone, and then it can diffuse in that water film from the area where it's sourced to a compliance point. It can also be sorbed into the water, which needs to do before it diffuses, I guess. And it can also travel by advection, just by the fact that these vapors are probably denser than air and then would sink towards the water table. And if they sank to the water table and were contacting it, they could actually dissolve into it and be carried away by the groundwater flow. So that's another mechanism by which transport can occur. They can volatilize to the surface and be gone, although EPA sets requirements on airborne contaminants as well, so you can't be outside that. And water infiltration can also wash it down. So that's, we'll really talk about two mechanisms of transport of the three. The two we'll talk about is diffusion in the vadose zone in the gas phase. We'll talk about advection due to washing out by water from rainfall in the aqueous phase, and we won't talk about natural convection by negative buoyancy, right? Being less dense than air, it travels downwards. So those are our processes. And so if we're to draw a picture of what that looks like, the first two that we'll talk about, the ones on the left, the only two we'll talk about. And so if you imagine having something that somehow gets into the vadose zone, then once it sits there, we know it's held by interfacial tension, interfacial forces. So all it can do to move is going to be by evaporating, essentially, volatilizing, and being carried off as a vapor that can travel in the air, which is a continuous phase in this, right? As you go from here to anywhere else, you can get there continuously by going in air between the grains. Second one we'll look at is by infiltration. So we'll look at diffusion first. We need to understand, well, actually we don't need to. We will use Henry's law. You've probably seen Henry's law in your past. Henry's law coefficient here is H prime. It's some funky units, which are atmospheres, meters cubed per mole. Very strange units. Concentrations in the water phase would be in moles per unit volume, typically. And this is partial pressure of the contaminant. And so this would say that the concentration in the gaseous phase, so this is similar to the concentration in the gas phase. It's related to the partial pressure. But it's of different units to the concentration in the water phase. And so because it's in different units, then this H prime term has units to be able to represent, to relate the two to it, and they tend to be strange. What we'll try and talk about today is that we can relate a non-dimensional Henry's law coefficient, which we'll just call H, which is equal to the concentration in the gas phase divided by the concentration in the water phase, the amount of the solute dissolved in water. And because these are defined in both the same units, then this has no dimensions. So we'll refer to Henry's law, but we'll use a slightly different form because it's more convenient. The second term that we'll need to use is the idea of partitioning. We talked about Raoult's law being, an effective solubility of component I as being equal to the mole fraction of component I multiplied by the free phase, the single solubility of component I. So TCE dissolved in water on its own with no other dissolved solute would be free phase behavior. And this is the term you'd get from a textbook. You know the molar concentration from your site data, as we talked about last time for Smithville, and from that you can calculate a lower reduced effective saturation because these compounds are all competing for the water to pick it up and dissolve it. Essentially the colloquial description of what's going on. So we'll talk about Raoult's law as well. So we need to be able to use that if we have multiple solutes. In terms of transport mechanisms, we can talk about diffusive transport. And this transport is actually diffusion. Right? We talked about diffusion and mechanical dispersion both looking the same. Skyscraper spreading out in a Gaussian curve as it progresses through time or goes downstream in an aquifer. One is true diffusion and one is just looks like diffusion. Mechanical dispersion looks like it is it's downstream. And you'll recognize the mass flux in Fick's first law being related to a concentration gradient, a diffusion coefficient, which is an effective diffusion coefficient. We called it D star before to represent the fact that it was in a tortuous porous media, and multiplied by the area which it passes through. So this is the effective gas content, volumetric gas content by volume. So when 100% gas saturated, then the gas content is equal to the porosity, right? Because there's nothing else, no water, so by definition. So again, what we do with this is we take a mass flux, we put it in conservation of mass, that mass in equals mass out, and what doesn't come into the balance is accumulation, which is essentially Fick's second law, and we get this. Accumulation is equal to mass in minus mass out, seen before. This happens to be an effective diffusion coefficient, and so we'll talk about exactly what that is. And this is a retardation coefficient, and it's not equal to, I guess, this is a gaseous coefficient. It's not equal to 1 plus d over phi kd, right? So just be, it's not that. It's going to be a gaseous diffusion coefficient. So maybe we should talk about each of these terms. First, the effective diffusion coefficient, because that's what describes what's going on. We'd expect that if in the picture that we had before, we had this portion that was just diffusing in all these directions, then physically what that looks like for us is if we take a section across here, it looks like this. So T1, T2, T3, etc. T infinity is just flat and of low concentration. And this would be C over C0. And this would be radius, I suppose. And so we need to look at what these two coefficients would be. Okay, one other thing. I guess we could also do this. We could divide both sides through by r. So this becomes 1. And now we're left with a component that represents the ratio of diffusion coefficient divided by retardation. And so since you know exactly what that meant before, was that if you have retardation occurring, then it means that the front doesn't travel quite as fast in the given time. It scales with the advective velocity divided through by retardation. And the residence time distribution that you'd measure in terms of the arrivals at this location would be delayed. And so that's exactly what happens here. It's not being driven by advection, but it's being driven by diffusion. And so what you'd expect is that this Gaussian curve, as it evolves, probability density function, would physically mean that if it's unretarded, if it's conservative, and there's no delay, then it might look like this at some time. If it's non-conservative and it's being sorbed onto the water and the substrate, then it would travel less far in that time. And you could calculate based on the equations we used, but using an effective diffusion coefficient, which is just reduced by a factor r. That's it, factor of 1 over r, I guess. So that's physically what the retardation coefficient would mean, although we haven't really said what Rg would be yet. So let's save that excitement for the future. Diffusion coefficient is a bit like our behavior in water that we talked about. So a swimming pool, but this is in air. It's going to be controlled by the diffusion coefficient of that compound in air multiplied through by some coefficient. Before, if you remember when we were talking about the aqueous coefficient, we just called it d star, and it was equal to omega d, I think, right? We use this omega term, which is the same idea. It's a tortuosity. It means as it goes from, as the crow flies, it can't fly as the crow flies, but it has to go on a much longer path, and that tortuosity is the ratio of the lengths as the crow flies to the actual length traveled, squared for some reason. And so values of this term here are not so easy to get because you don't know what these terms are, the lengths, but there are empirical correlations that define it in terms of the volumetric gas contents and the total gas contents. So I guess total gas content would be when it's 100% gas filled, which would be the same as the porosity, right? Which is typically something like 10 to, it's decimal, 0.1 to 0.3. as a fraction. And so if you know what this is, then you get this from the reference table in the library or online, Wikipedia, or NIST table of chemical coefficients. You get this from knowing how much the gas content is. So I guess you also know that the volumetric gas content plus the volumetric water content is equal to the porosity, right? If there's just two parts that are filling the porosity. And so if you know the gas content and you know the porosity, well, I guess you just need the gas content for this. If you knew the water content, then you could also use that here. And so as an example of that, you could calculate what this diffusion coefficient was in the soil column. This is a capillary pressure versus saturation curve, or it's actually an elevation versus saturation curve, but it's the same. We can relate elevation to capillary pressure, as you know. And if you look at the this magnitude here would be water content. This magnitude here, if you can see it, is theta G, gas content. And so this looks like it's about 5%. So this means that the porosity for this is about 30%. If this is 0.25 plus 5, or 25 plus 5. And so if you know what these gas contents are, you can use Millington Quirk. You know what this is, to the power of 7 over 3. You know that the total gas content is going to be 30%. This has to be not a percentage but a decimal in this. So if you use 25%, you calculate the value of tau, 0.32, and if you multiply tau by the gas constant for TCE, which apparently is 8.1 times 10 to the minus 6 meters squared per second in air, quite fast compared to water. You multiply them out, you get an effective diffusion coefficient. If you reduce the gas content as you go deeper down to 5% instead of 25%, it comes out to be a smaller number, less cross-sectional area for it to flow through. You'd kind of expect that. And if you're looking for the diffusion coefficient as you go into the water, you need to use D star for diffusion coefficient in water, which instead of being something of the order of 10 to the minus 6 meters squared per second in air, this is in air. I said before that the diffusion coefficient in water is something of the order of 10 to the minus 9. So 3 orders of magnitude slower than it would be in air. So presumably it takes longer for odors to travel than they do in air. So you can calculate what those diffusion coefficients are, and if you know those diffusion coefficients, you should be able to calculate from the probability distribution function exactly how it might travel if it's not retarded, if R is equal to 1, in other words. So we're solving this equation. We now know how to get this. How do we get this value here? So I'm not sure we'll derive it, but we'll make a comment we've talked about. Let's come back to that. Let's just define the term, not derive it. The basic idea is this. If we call it, we've called it the gaseous retardation coefficient. It looks a bit like the ones we had before. This looks kind of familiar, except for the extra term, which is our Henry's law. We said that our non-dimensional Henry's law is equal to the concentration in the gas phase divided by the concentration in the water phase of a solute, dissolved in air, vaporized in air, or dissolved in water. So that's what this term here is. So the idea is this. If you have a DNAPL, then we know that from Raoult's law, the effective saturation of that phase will be equal to the mole fraction times the free phase solubility. I use saturation and solubility interchangeably. I shouldn't. Solubility. I meant to say solubility. So the solubility of the free phase with no other contaminant in water is given by some amount. I guess we just saw that it's something of the order of 10 to the minus 9 for TCE. And so if we know that value here is 10 to the minus 9, then if we know the mole fraction, we can calculate what this is. So this is what would sit in the water. And so the way that retardation is usually computed is that you affect that there's an equilibrium between the solid grain and the water. And this is what we've called before C star, right, on the solid. So this is an equilibrium. And so that is what's governed by KD. Remember that KD distribution coefficient was equal to the concentration on the solid relative to the concentration in the water, by definition. And so the water is in touch with this and a film that covers the whole of the grain's pore space. So there's some portion of this which is in equilibrium between the concentration in the water and that which is sorbed onto the solid. So that's one coupling. The other coupling is that there's equilibrium between the concentration within the water and the concentration that's in the air phase, which is continuous in the vadose zone. So that part is this. And so there's a defined concentration in the water, and through Henry's law, there's an equilibrium between the water and the air, and that's given by the second term. And so these two terms effectively represent water solid, partitioning for the stuff dissolved in the water, and this is air water. And they're both for partitioning. And so I guess the common medium is the water. The water is what holds the defined solubility according to Raoult's law. If there's only one component, it would be this. This is the solubility that defines this, which is SI. And then this controls its equilibrium with the air and its equilibrium with the solid in both places. And so this gives us a value which is different from the one we had before. So this is for transport within the vadose zone. And that would be what would control this rate here that we're talking about. So if you're looking at how quickly it would travel in the continuous air phase from a source to some compliance point, then it's controlled by this retardation factor and this diffusion coefficient. And you have the equations to be able to do that. Okay. All right? So that's a key issue. If we look at magnitudes of those and assume that we know that we can calculate this non-dimensional Henry's law coefficient, concentration in gas over the concentration in water. We'll come back to this later. If we take a value for this for TCE and an organic carbon partition coefficient, and I guess we'd need a fraction of organic carbon, a bulk density, and a volumetric moisture content and a volumetric gas content. So these must mean that the porosity is, don't tell me. How much? Sorry?
Said to not tell you.
Said tell you, fine. You take me literally, I know. And if you have a defined, so if you have these as constants, this is just to illustrate that. So if you calculate the, what is this? This is air-water. This is water-solid. These coefficients here, right? These coefficients. And you calculate what the retardation coefficients are, then obviously the gaseous one, the air-water one, isn't controlled at all by the fraction of organic carbon, but the aqueous one is. And so if you calculate the retardation just due to the aqueous component, it's equal to 1.33. If you calculate KD is equal to organic carbon partition coefficient times the fraction of organic carbon, assuming that all the partitioning or sorption is on the carbon in the soil, then if it's a 100% or 1%, so we said that you shouldn't, the boundary was the middle, which was equal to 0.1%. So this is less than above this, and this is more than below it. So it would be presumably applicable to use this equation here. So this is actually okay, but this is not. Then the retardation factor for this would be 1.33 plus 2.27, which is 1.6, plus 1 is 2.6, right? So you're just adding this plus 1. This term here. And if you change the fraction of organic carbon, so there's not very much, well, there's a small effect. I guess this would be a small retardation. We looked at Borden. They're roughly of this order of magnitude for aqueous retardation coefficients. But the big change you get is if you have a lot of organic carbon. And if you have a lot of organic carbon, the partitioning from the water to the solid is big, and therefore it makes this a big number. 30 times slower than if you had it going otherwise. I guess 15 times slower between these two. So there's a big shift in those two. Okay? So that's how you can calculate that. So that begs the question, then what happens if you have something locked up in the vadose zone, like we've talked about, and that this can diffuse in the vadose zone, or it also can contact the groundwater zone, and it can also diffuse in groundwater. So we know it can be carried by advection at some advective velocity, but let's assume that that is equal to 0. So it's stagnant underneath. The water table's flat. And so you have a measuring well that is present both in the saturated groundwater zone and also in the vadose zone. Same distance away from both of these things, the spill site. You'd probably expect that the arrivals of the components in each of these locations would be in the same order, not necessarily the same time, because this would be responding to the gaseous distribution coefficient, and this would be responding to the aqueous distribution coefficient, or water, I'm not sure. We use aqueous and water. This one is 1,000 times faster than this, right? 10 to the minus 6 versus 10 to the minus 9 in water. And so we can define the sequence in which different contaminants will arrive at these downstream locations based on the magnitudes of the retardation coefficient, because it's controlling this behavior of diffusion in terms of this scaling here. So the larger the retardation coefficient, the more delayed the arrival will be at some downstream location. And we note that these retardation coefficients are different in the different materials, right? This is the one which will govern behavior in the saturated zone. And this is the one that will govern the behavior in the vadose zone. And so we can do a little thought experiment to look at this. And for 3 compounds, and we know what the organic carbon partition coefficients are, we can calculate distribution coefficients, and from each of these together with non-dimensional Henry's law. So these 3 things are the basic data we have: organic carbon partition coefficient, K sub D, and also Henry's law coefficient. And if we have each of these pieces of data, and we have some information on the volumetric water and gas constants, and some data about the density of the aquifer, which doesn't change very much, we can calculate what each of the aqueous retardation coefficients are and the gaseous retardation coefficients. So if we calculate what each of these values are, then we end up with these numbers here. So it means that the lower the retardation coefficient, the earlier the arrival. So in the saturated zone, we're governed by the aqueous retardation coefficient. The fastest moving phase is that dissolved in water is methylene chloride. The next fastest is this, and the slowest is this, most retardation. So the arrival time in the groundwater piezometer will be 1, first, second, and third. And that's just according to the magnitudes of the retardation coefficients are increasing monotonically through these 3 different compounds. If you look at the gaseous one, the first arrival will be this, but the second arrival will be this. And so for this one, it will be this, and then this to the third. And that's all this is saying here. So the order arrival will be methylene chloride arrives first, TCA and TCE. And it's different in the 2 different wells. So a perplexing situation perhaps that you might not expect, but I guess it's driven by the fact that there's a free parameter in here, which is the Henry's law coefficient, which doesn't appear in here, and it changes the magnitudes of the retardation coefficient, and therefore the order of arrival. Okay? At Oregon Institute of Technology, Oregon Tech, I think. I don't know. It's not Oregon State, and it's not University of Oregon. They have a big artificial aquifer that you can construct, which is 10 feet deep, 3 meters, and 10 meters, 30 feet wide, 30 by 30 by 10, which they can make an aquifer out of sand and then put into it little capillary measuring tubes to be able to measure the concentrations of different components. So this is an experiment with a portion of that area which has dug into it a cell which is 4 inches by 4 inches by 4 inches. Oh no, I guess that's not right. I guess you know exactly where it is. It's 1 meter deep. It's a small sample that's dug in, which is at residual saturation in the sand aquifer. And they're looking at what happens over 1 day and over 3 days by going into it and sucking air out of here and using a gas chromatograph to measure what the individual concentrations are, and then contouring it in vertical section view rather than plan view, as we did for the Borden site. And you see that the biggest concentrations are close to the source, and they get progressively less as you go further out. And if you look at the behavior for methane, butane, and TCE, 2 gases and a liquid which then vaporizes, then you can tell from these that 2 of them have roughly the same retardation coefficients as each other, and this one, the gaseous retardation, is less than the gaseous retardation for methane. TCE, right? Quite evident from the fact or rather retardation other way around, right? Good. Thanks for telling me. And you see it again here. So these are moving slower, retardation has to be lower. And so you can look at those values, and I think that's what's done here. You could calculate those retardation magnitudes just by looking at how far it should have gone for conservative gas and how far it's gone for one that's been retarded. And the Henry's law coefficients turn out to be in this order for the three different coefficients. And so since we know that the gaseous retardation coefficient is proportional to 1 over the Henry's law coefficient, then a big Henry's law coefficient means a small retardation coefficient because it's 1 over scaling in both of the terms. And so that's what's echoed in those values. Okay. So, how are we doing? So we know how to do that. I guess the final thing we might be interested in knowing is that we've made this point that the Henry's law coefficient is really the concentration in the gas phase divided by the concentration dissolved in water. We've also called CWC aqueous. Same thing. So how do we know exactly what this non-dimensional Henry's law coefficient is that we want to use in this expression here? And so the analysis is pretty straightforward. Flashback to 303. This is our own definition of what we want this non-dimensional Henry's law to be. It's the concentration in the gas phase divided by the concentration in the water phase. If they're in the same units, then they have to be dimensionless. And Henry's law coefficient represents an equilibrium. It represents an equilibrium between what's dissolved in the water, the solubility, I guess, in the water, and the equilibrium concentration in the air that sits above that. That's the definition of Henry's law. And so the non-dimensional Henry's law, which is what you'd get from a textbook, a reference book, is the vapor pressure of that coefficient, TCE or whatever, divided by the concentration of that coefficient in water. And this is what we've called the solubility, actually, right? Could be mass per unit volume, or it could be a molar concentration. So perhaps it's a molar concentration. Don't get PSD, but this is vapor pressure, ideal gas law. Density, ideal gas, universal gas constant divided by the mass of 1 mole, the molar weight of a compound. If this is just the gas constant for that particular gas, then you don't need, it's a different value for every single compound. But if it's if you use a universal gas constant, then it's good for every compound because it's normalized by the mass. And this is temperature. We know that temperature should be in Kelvin, so we know that. So what we can do is we can substitute the ideal gas law for the vapor pressure here. If we do that, then we get this term here. This is the ideal gas law here, and this term. I guess these terms are the ideal gas law. And if we merely partition this, so we keep this term here, and we take the other terms on their own, whoops, you get this. And so if you divide Henry's law, if you divide both sides by the universal gas constant times temperature, and the universal gas constant times temperature, then this goes to 1, obviously, and you're left with this term here. So this is the concentration in water. So this is moles per unit volume. This is mass per mole. So the product of these two gives you concentration in of the gas, I guess we've called it. So the density of that, sorry, these two here give you the concentration of that gas, right? The density of that particular compound divided by its molar weight gives you gas content. And so these two terms are just the values of the Cg over Cw. So in other words, which is Cg over Cw by definition. And you can check out the individual units of that. So we can get this value here. We know all of these components. So if we want to, we can use that to calculate exactly what this Henry's law coefficient is. So if we take TCE, the Henry's law coefficient apparently at 20 degrees centigrade is this, which is 9.1 times 10 to the minus 3 atmospheres meters cubed per mole. We have the universal gas constant as 9.82 times 10 to the minus 5 atmospheres meters cubed moles Kelvin, and we have temperature in terms of Kelvin. And if you substitute those into that, you get a value of this non-dimensional Henry's law coefficient to be about 0.4, which we saw earlier, right, as well. For TCE, where we talked about Oregon, we plucked it out of the air and didn't justify it. So it's possible to get it from there. So now we have everything we need to be able to calculate H to go in the gaseous retardation coefficient. So I won't talk about that. Other values, concentrations, won't talk about that. Yeah, that's all I'll talk about. So we mentioned before that we could think about two different ways of representing the behavior. One is what we've exclusively talked about so far, and that is by diffusion. So we know how far it goes is controlled by the gaseous diffusion coefficient, and the rate at which it does that is controlled also by its retardation. So we know that D star G and RG are two terms that control this. It turns out that by far the biggest loading in these systems is driven by dissolution by water, bless you, and advection down to the groundwater table, and then advection in the water table from that. So the biggest loading, this will certainly escape to the atmosphere, but it won't give much loading, as we'll find out later, to the groundwater table. And you're probably most interested in whether, if you get a drinking water supply by taking out water from some location, whether you're dragging stuff into that from upstream as a plume goes progressively further and further downstream. So this ends up being the major contributor. So how do we do this calculation, and how do we use the various values of retardation? I guess we won't use this when we do that, but we'll use retardation coefficients. So what we'll do is a couple of simple calculations, and they're actually for Borden, the site that we looked at for the natural gradient tracer tests. And that is this. So if we think about starting with our smear at some distance, it's raining in Canada, and so that rain will give you basically a velocity of infiltration, a length per unit time, which is how you define infiltration rates. 6 inches of rain in a day would be a rainfall that all goes into the ground in one day. And we can define the advective velocity of that if we make some assumptions. So what we could assume, I suppose, is that if we have a porous medium, and if we know that that porous medium has a skin of water around it, and that volumetric water content is what we've called VW, theta W, right? So if water completely fills the pores, then this is equal to the porosity. But if you think about rainfall coming into this moisture content is probably at some kind of pseudo steady state. If you look at it averaged over a year, it probably stays roughly the same amount, and then from year to year, it stays at the same amount. It might go up and down as you get infiltration events, but on average, it might stay at some constant. So if you take that as an assumption, then any water that would be coming into this, to keep it at the same moisture content, that water must just flow within the water film, which is present as the connected pathway between upstream and downstream. And so if the water that's coming in as rainfall is only flowing in the cross-sectional area that's water-filled, then it's really defining a velocity that it goes from the surface to the subsurface, which is kind of an advective velocity just by going in the water. And so if you divide the rainfall intensity, inches per day, centimeters per second, I guess it would be meters per year would be a good value, divided by the volumetric moisture content, the actual velocity at which it's going in the subsurface, if it's 6 inches per year in rainfall, and the volumetric moisture content is 10%, then that means it's traveling at 60 inches per year because it's multiplying it by a factor of 10, right? Just like advective velocities. So that would be the velocity at which it would travel. So VAW. But if you want to calculate the loading, the mass loading of the dissolved contaminant as it arrives down at this base, that mass loading is going to be given by Darcy's law multiplied by the concentration. So this is the mass flux. I guess this is what we've called before m dot. I think it's a mass flux per unit area, but don't worry about that. And so the Darcy velocity is just the advective velocity, which we have here, multiplied through by this volumetric moisture content, and that gives you this Darcy flux. And so if you want to calculate the mass loading, it's the Darcy flux multiplied by the solubility, just as you've done in some of your assignments before. It's kind of confusing taking an advective velocity, then re-multiplying it by the volumetric moisture content to get it back to the Darcy velocity. This is basically the Darcy velocity. And so if we want to calculate the loading that will occur at the groundwater, we can calculate it from this expression here. So one thing is the rate at which it would arrive, and I guess the rate at which it would arrive, the velocity at which it would arrive, V advective actual would be equal to V advective divided by the retardation coefficient, right? As it goes through the soil, it should go at this velocity. This is what you've calculated from this. This is just a physical term. But it's going to get sorbed onto the matrix, and then for it to be delayed, just like the plume is delayed elsewhere. And so, here's a good question. Is this the aqueous or the gaseous retardation coefficient? Don't answer me. What do you think? Bummer.
That's what she was gonna say.
I know, that was going to be the next one. That was going to be the next one. I know. Yeah. No, it's in the water, being carried in the water, and the only place it can attach itself in equilibrium is the solid grains. So, because the gas phase is mobile, so it's going to be that. So you have everything to be able to calculate that. Don't need that. Two examples, I guess, or an example to close out. Again from Borden. They actually did this experiment. So you saw the one in the saturated zone. What they did was go into the saturated zone, dig a hole, put in a little packet that was replaced sand, that was carbon tetrachloride, sodium chloride, PCE, can't remember what the other compound was. And they just let that get carried downstream by advective velocity in the water. So that was the data we already looked at. Did exactly the same experiment above the water table. I guess I know here from the picture below, water table must have been, looks like it was 3.5 meters deep. Something like this. So you dig a hole, mix up some of this stuff along with other compounds in sand, put the sand back and backfill on top of it with pristine sand, and then look to see what happens over multiple years. There's no advective transport in the vadose zone, right? There's no reason that the air needs to travel laterally. So it's just going to stick there and it would diffuse, just like we talked about in terms of this kind of behavior a long way back, covered a lot of ground. It would diffuse just like this into the air. It may contact the water table, but the real source, we think, by which it's going to be transported to the groundwater zone is by being washed out of this smeared chimney, as we've always talked about, water going through here and carrying it down to the groundwater zone. And so we can calculate both how long it would take to get there and in what mass loading, because you have those two expressions. So this is the geometry. This is what was done. A liter of TCE and a bunch of soil turns out to be basically at residual saturations, maybe saturation of 5 or 10% within this little volume. How long does it take to reach the water table? The aqueous advective velocity is the infiltration rate divided by the volumetric moisture content. Volumetric moisture content is 10%. It rains 0.5 meter a year there, which is 18 inches a year. Not so much actually. Or this is the actual infiltration. I guess it might rain more, but some of it might be runoff. So this is the amount that goes into the ground. I bet you it's probably more like here. We must get 40 inches a year of rain, right? 1 meter and a bit. Not so different. So 0.45 meters a year divided by 0.1 is multiplying that by 10. 4.5 meters a year is what it travels. We could get fancy and do V actual is equal to V water advective divided by the retardation coefficient. Is it the gaseous or aqueous retardation coefficient? Come on. Fine. At least we're in good spirits. So anyway, if it's 4.5 meters a year and it has to go down 2.5 meters, it only has to go down 2.5 meters because the water here that's coming in here is replacing water that's already here, which is replacing water that's here. So right, this immediately as this comes down, it starts pushing water from this location downwards, right? Because it's already a continuous water column. So as soon as it comes in here, it motivates this to start moving. And so it has to travel 2.5 meters, travels 4.5 meters a year, that's 6 months. If the aqueous retardation coefficient is greater than 1, then it will take longer, proportionately. So instead of half a year, if the retardation is coefficient is 2, it'll take a full year. So it'll take it back to this magnitude. And if we want to calculate the loading of that part of the aquifer, so how much stuff arrives here, then after half a year, which it will take to travel, right? The travel time is half a year. And then once it's half a year, the plume will have arrived. It will keep on arriving at that constant mass loading. It's going to be equal to the Darcy flux, which is just what? Q infiltration, which we defined before, multiplied by its solubility. So Q infiltration is 0.1 times 4.5, which is 0.45 meters a year. This is Q infiltration times whatever the solubility is. Just one component. Free phase solubility of TC is something like 1100 parts per million. So you multiply these two and you get some amount which is 0.5 kilogram per year per meter squared. So this is, if you draw it in perspective, this would be the mass loading, 1 meter by 1 meter. And of course, if this was spread out, then that would be multiplied by whatever the cross-sectional area would be. That's it. So you just need to know, well, you don't need to know how to do that, but you now know how to do that. Here was a model doing exactly the same thing. In preparation for that, I guess it was 5 meters, not 3.5. Doesn't matter. 2 meters above instead of 1.5, which I had. I guess that's, yeah, it's 5 meters. And if you do the calculations to look at that, this is this. So this is the little package of stuff that's put below ground. This is kind of axisymmetric symmetry. So this is a center line. So if you look at this in what it looks like in plan view, this is like a slice of cake. This is the center line. This is the packet of stuff that's in the ground. Right? So if you're doing a numerical model, you've got this cylindrical package in the ground, which is surrounded by an infinite medium. One way to make your calculation much easier is to look at some symmetry in that system. And so one line of symmetry is that it's radially symmetric. If you take a cross-section down through it, a slice of cake, and look at it in every single azimuth, the concentration, the plume concentration would be exactly the same as you go around 360 degrees. So it means that you can solve this thing by just looking at one slice, and so it takes a three-dimensional problem and makes it into a two-dimensional slice. Horizontal direction and vertical, just R and Z, I guess. And so that's what this section is. It has a center line because it's centered on here, and it looks at the concentrations of this stuff, TCE, as it goes outward from this. And it looks at two cases. One where you have it coming from here after 6 months and 1 year. And the two cases are when this is open. And so this is allowing infiltration to fall down here. And the mass that comes in 6 months is 6 kilograms, dissolved from here, and in a year is 16 kilograms, so slightly more. So I guess that makes sense, right? There's a certain lag because it's a travel time. And so this is a smaller amount because in the first part of this time, none of it's arrived yet until it gets to steady state. And then once it gets to steady state, then it will continue being, this is a cumulative mass that arrives. So it continue coming at the same rate once it's broken through. And so this would be in a year and a half, or in 2 years, that's an easy calculation, it'd be roughly 32 kilograms, slightly less. Slightly less because it's 0.2 less, and also because it's not quite double because what we said about the travel time to get here. And the other case they looked at was what happens if you put a liner on the surface. So if you put a geotextile or something, so now the rain that comes down doesn't go in there, it goes off to the side as runoff. And so this area here is completely dry. No longer do you have stuff washing through here and washing it down because it can't get into here. And so if you look at the amount that gets delivered to the water table, there is an order of magnitude less. 0.35 versus 5, and an order of magnitude or less again. So a very simple demonstration, I guess, to make the point that infiltration compared to this analysis would also include diffusion. Actually, this has to be diffusion, right? This is diffusion, what's going on here, plus advection. So diffusion isn't really affected. It continues even if advection is occurring. This happens. But the amount of material that is transferred to the water table by these finite concentrations, which are transported by diffusion. So these are order of magnitude changes in concentrations as you go back from here. This would diffuse into the groundwater zone, but the amount that goes in due to that is trivial. So if you can get rid of the amount that is washed into the groundwater zone, then you immediately reduce it. So I guess that's it. That's what we'll talk about. So to get to the groundwater zone, it has to go through the vadose zone. We've talked about it getting hung up there, being able to volatilize and diffuse and perhaps move to the atmosphere and be lost to the atmosphere. As it turns out, if it's diffusing laterally, it doesn't put much loading on the groundwater table. Most of the resources that we take out of the ground would be in the saturated groundwater zone, so we perhaps don't care so much about this. But we do worry about what would go into the groundwater zone here and be carried downstream. And so that's why we have to be able to calculate how quickly it gets to the groundwater zone and in what loading. So now you can do that. So now you've done everything we need to do in this class. And so the wrap-up parts we'll do, we'll talk about modeling, how you do models like this in a very straightforward way in one period. And then we'll talk about how you know what the concentrations and distributions of these different components would be by drilling holes in the ground and sampling and by using geophysics. That's it. That's what we've got to do.